Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Faiz bin Ahmad Fauzi. My matric number is B051820092. My supervisor is Dr. Muhammad Rizwan Jamli. The title of my PSM2 project is Experimental Investigation of Toolware Characteristic in Turning of Mnemonic C263 Alloy. Mnemonic C263 alloy material characteristic is precipitation hardening, corrosion resistant, excellent strength, great ductility and high temperature. The application of material is in aerospace industry, gas turbine blades, power generator and heat exchangers. For problem statement part, most prevalent issue that other researchers encounter during cutting the mnemonic C263 alloy is cutting too short life cycle when machining the alloy that will result in tool wear. Besides that, most of the mechanical energy used to remove materials becomes heat, which generates high temperature in the cutting region. The objective of this study is to analyze the tool life while turning the mnemonic C263 alloy using PVD coated inserts under flat condition. Besides that, the objective is to evaluate the tool wear mechanism and their wear failure and to create a statistical model for tool wear to validate the cutting parameter. For the methodological part, flowchart is used to represent the overall experiment procedure. Before we run the experiment, we must select first the cutting parameter that will be used. The experiment cutting parameter was chosen based on the literature and handbook guidelines for turning process of mnemonic C263 alloy. The final cutting parameter is cutting speed, feed rate and depth of cut. For the cutting speed, the lowest is 60 mm per minute and the highest is 120 mm per minute. For feed rate, the lowest is 0.05 mm per revolution and the highest is 0.15 mm per revolution. And lastly, the depth of cut, the lowest is 0.3 mm and the highest is 0.5 mm. The turning process will be carried out until the tool wear reach VB 0.2 mm. After that, ANOVA analysis will be conducted and validation of the mathematical model will be the final part of this experiment. The experiment only consists of 3 equipment, which is CNC lathe has ST20, toolmaker microscope and flat coolant system. The CNC lathe is used to machine the turning process of the experiment. For the toolmaker microscope, it is used to identify and measure the tool wear so that it can be noted and recorded. And finally, for the flat coolant system, it is used to reduce the temperature that will be generated during machining the workpiece material. The workpiece material that were used in this experiment is mnemonic C263 alloy in a cylindrical form. The diameter of the alloy is 90 mm and a length of 150 mm. The table shows the element and content that were in the mnemonic C263 alloy. The cutting tool that will be used in this experiment is PVD coated carbide insert Sunvix type with ISO number CNGG 120408 SGF 1105, and for the tool holder used for holding and placing the insert is DCLNR 2020K and 12. For the result and discussion, the tool life of the all 17 run are shown. The maximum tool life occur on run number 11 with the reading of 19.25 minute. And for the minimum tool life occur on run number 10, which is 1.97 minute. For the tool wear progression part, tool wear commonly occurs in metal cutting in this experiment. The coated carbide tool wear progression was recorded using the toolmaker microscope. The tool life of the cutting tool influenced the tool wear progression because longer tool life brings gradual wear progression. Based on the figure and graph from the cutting parameters of cutting speed 60 mm per minute, feed rate 0.1 mm per revolution, and depth of cut of 0.3 mm, the progression of wear involves three stages, namely early, middle, and final stage. Intense rapid wear is shown in the early stage, and the wear slowly increases at the middle stage. At the final stage, the rate of wear accelerates rapidly. The experiment was carried out with the utilization of mixture parameters that were produced by the RSM analysis box beacon. The ANOVA analysis was conducted to determine the relative relevance of individual tool life characteristics. The ANOVA analysis shown is the one that insignificant model has been removed so that it will simplify the model and increase the precision of prediction. The new tool life model's F value was calculated using the new ANOVA method and was calculated to be with the value of 99.9. This indicates that the model was significant. The data also shows that the lack of F value of 1.45 implies the lack of fit is not significant relative to the pure error. There is a 37.92% chance that a lack of fit F value this large could occur due to noise. For the statistical summary model of the tool wear, it shows that the predicted R square of 0.9441 is in reasonable agreement with the adjusted R square of 0.987, with the difference is less than 0.2. Adequate precision with the reading ratio of 31.220 indicates an adequate signal. Model diagnosis plot shows that the normal probability plot of the residuals for tool life demonstrates no evidence of violation as each point in the plot follows a straight line pattern. The residuals are plotted against the ascending predicted response value for tool life. It verifies the constant variance assumption. The expanding variance in this plot demonstrates the necessity of a transition. It is recognized that residuals normalized to projected tool life values exhibit no discernible pattern and are randomly distributed positively and negatively. This demonstrates that the model is adequate. For the second graph shows that the plot of residuals versus predicted for tool life. The residues versus plot indicates no noticeable pattern, unusual structure pattern, or unusual presence in the data. It is understood that the residuals standardized with respect to the predicted values of tool life is distributed in both positive and negative directions. All the point is plotted within the 3 sigma range. This implies that the model is adequate. One factor plot of cutting speed versus tool life shows that the incline of the gradient line shown on the tool graph in relation to the cutting speed is enormous. This demonstrates that there is a considerable relationship between the cutting speed and the tool life value. As the cutting speed increased from 60 meters per minute to 120 meters per minute, the tool life pattern shows a decreased trend. For the second graph, it shows the influence of the feed rate to the tool life. The graph of the one-factor plot shows that when the feed rate is increased, the tool life of the coated carbide will be decreased. This shows that the tool life was significantly influenced by the feed rate. This condition may happen as a result of the cutting force that is applied to the workpiece as well as the cutting tool while the workpiece is being machined. The 3D surface model graph of tool life that demonstrates the interaction between two variables, particularly cutting speed and feed rate, and the influence of depth of cut and cutting speed. From the cutting speed and feed rate graph, it shows that when the minimum cutting speed is associated with the minimum feed rate, the tool life value will be increased. Similar trend will also can be found in the influence of depth of cut and cutting speed on the tool life of coated carbide tool 3D model graph. It shows that tool life improves as the depth of cut and cutting speed are reduced. For the model validation experiment, it was carried out on a selected data as shown. The tool life equation was derived from the ANOVA analysis that have been done previously. For the validation cutting parameters, the cutting speed is 180 mm per minute. The feed rate is 0.145 mm per revolution and the depth of cut 0.38 mm. This data was chosen from within the cutting parameter process range and was used to calculate the projected tool life values. The result of the validation experiment error percentage for tool life from the theoretical value it is 3.5521. From the experimental value it is 3.600. The error percentage is negative 1.34721%. Among the experiment data and theoretical values, the values were likewise very comparable to each other. As a result, the validated combination of the obtained ideal process parameter for tool life. As for conclusion, the three main objectives of this experiment were able to achieve. Firstly, the highest tool life obtained during this experiment is 19.25 minutes, while the least is 1.97 minutes. Cutting speed is the most influential parameter on tool life, followed by feed rate and depth of cut. Secondly, it is found that the flank wear progression can be classified into three stages, which is initial, middle, and final. And lastly, the mathematical model that were produced by ANOVA analysis of this experiment is able to achieve by using the RSM method box beacon.